Now, any arbitrary code can go inside the for loop. In fact, we could put if statements inside the for loop. This is known as nesting flow control. So let's see an example of this. Let's say we wanted to write a function that would take the species of a penguin and an island as arguments, and it will return how many penguins of the species, that specified species, live on that particular island. And so let's write a function called countPeng, and it will take as arguments the species of the penguins, penspec, let's say, and the island, so penisle. And since we're going to be using the Parma Penguins library, let's make sure to silently load Parma Penguins using require. And now I'm going to be counting, right? We have to determine how many penguins, which means I'm going to be performing an accumulation task where I will go through the rows of the penguins dataset which match the species and the island, and every time I encounter such a row, I will add 1 to my number of penguins. So let's say we will have a variable which will keep track of how many penguins are there that match our conditions, and obviously we will initialize it to 0. And now we need to do a for loop and over the rows of the penguins. And let's say we want to do it with indices, so we will have a variable index, and now I need a vector that starts at 1 and it goes up to whatever number of rows there are in the penguins dataset. So I will use seek as we did before, but I don't know what number to put here for the number of rows. So we should use the nrow function to determine how many rows the penguin dataset has. And then this index will start at 1. In the first iteration it will be 1, and then 2, and so on, and it will go all the way up to the number of rows the penguins dataset has. And this is an important aspect of good programming practice. You should not hard code. So it would be bad practice to determine the number of rows and actually enter the number here, because what if the number of rows in the penguins dataset changed? Let's say we had an update and we got more data, and now we have many more penguins than we previously had. So in order to keep your code general and flexible, it's actually, instead of entering specific numbers or of the sizes of data sets and other aspects, it's better to use functions like length and nrow to adaptively determine how many elements there are. And now we want a conditional statement where we will check whether this particular row matches the species that have been specified and the island that has been specified. And so we will get the penguin species column, and we want that particular element of the species column, and that should be equal to the specified penguin species. And I will put a parenthesis. It's not really necessary, but I will do so anyway. And now my second condition is going to be the island column, and I will take the IDX row of the island column, or the IDX element of the island column, and check whether it's equal to the island that has been specified and now I have two conditions. I need to combine them with a Boolean operator, and in this case we want and, since we are looking for penguins that are of that particular species and live on that particular island. And if this condition is true, then I have found one penguin that matches, and so I should accumulate. So I should increment my penguin count by 1, and then I can just return the total number of penguins. And let's see if this works. So we can call our function, and let's try Adelie penguins on the Biscoe Island. And there are 44 Adelie penguins on the Biscoe Island. And the main thing that we're doing differently from the previous for loops we wrote is that we are nesting an if condition inside the for loop. In fact, it's possible to nest for loops inside for loops. And so let's say what we wanted to do was we wanted to actually produce a data frame that would contain as columns all the species there are and all the islands there are, and then compute the number of penguins in each species and islands. This is something that one could also perform using dplyr. But let's just say here we want to do it ourselves and not use dplyr. So how would we go about doing this? Let's first give our function a name. So we want something that will get the penguin populations, and it'll be a function, and it'll have no arguments, since I will load the Palmer penguins data set. And it does just one thing. It figures out how many combinations of species and islands there are, and then makes a data frame for each combination, where each row is a combination, and then there's a column for the number of penguins for each combination of species and island. So the first task is I need to determine what are the species, what are the different species there are. And if you recall, dplyr has a function known as distinct, and what distinct does is if you give it a column name, it tells you how many distinct unique values there are of a particular column. And there is a related function known as unique, and what unique will do is if you give it a vector, it will return each unique value. So if there are multiple occurrences of a value in the output or what is returned, it'll occur only once. So let's try it out. So the penguin species is going to be unique in the penguins dataset and the species column. And let's just to see how unique works, let's print this peng specs out, and I can call my get peng pops function. It's not complete yet, but it'll print out the result. So you can see here it's basically giving us an element of length, a vector of length 3, and that means there are 3 unique species on the island, and it's giving us the names of those species. Now I could use unique again to determine how many unique islands there are, and I will take the penguins data set and use the column, use the island column to determine how many unique species there are. So now we know have two vectors, one for species and one for islands. And obviously, since we want all the combinations, we are going to use for loops to go over these different combinations. Our next task is to initialize the data frame that we're going to populate with the combination of the species and the number of penguins in each combination. So this data frame will have three columns. The first column will be species, the second column will be island, and the third column will be the number of penguins. And so let's start to initialize this data frame. Let's call it pen counts, and we'll use the data.frame function. And the syntax of data.frame is you give a column name. So we'll say species is equal to, and you give a vector of values that will go into that column. And here it will be a vector that's a character vector. So we use the mode argument of vector to initialize a character vector. That will have the length and how long should this vector be? That's the number of rows of this data frame. And that's going to be equal to the number of combinations of species and island. So I have 3 species and 3 islands. And so I actually need to compute the number of combinations, because that's going to determine how many rows this new data frame that I'm creating will have. And it's going to be equal to the length of the peng specs, a vector that contains a unique species, and the length of the peng isles vector, which contains the unique islands. And note here that we are not hard coding anything. We are not entering 3 times 3. We are determining the lengths from the functions provided by our, like length and unique and so on. And this makes our code flexible and general, where if the number of species were to change in the data set, or if the islands were to change, our code would still work. And so now the length is going to be numcoms, and then I will have another vector the same way for the species, the islands, and it's also going to be a character vector which will have the same number of rows. And then I will have a column, let's call it n, which will be a vector of mode numeric instead of character, but it'll have the same length, which is the number of combinations of species. And having initialized this data frame, now I can write my for loop. So what I would like to do is I would like to create each combination. So first I should have a for loop of penguin species in the peng specs vector. And then for each species that I have, I should iterate over all the possible islands that there are. And so I will do a for loop over the island. So I will do peng isle in peng isles, next I would like to know where I am in my which row of my data frame to update. So I will need an index variable, and so I will also initialize an index variable, which is basically which row I'm in. at 1. So this will keep track of which row I'm in. And then what I can do is I can determine the number of penguin species for this particular combination of species and island using the function we wrote previously, which was our countPeng function. And we can use the number countPeng function to figure out for this combination of species and island how many penguins there are, and assign this to numpengs. And next I should update my data frame. So I will take pen counts, and in the index is telling me which row I'm in, and the first column is the species. So I will say peng spec is the species. So I'm entering what species it is, and then I will take the same row, and the second column will get which isle it is, and then the third column will get the number of penguins there are. And I must remember to accumulate, that is update index. So I will take whatever is the value of index, add 1 to it, and save it back in index, so that in the next iteration index will have value 2, and so on until we reach until we have covered all the combinations. And then after this nested for loop, where I have a for loop inside a for loop, I can go and return the penguin counts, and now we can run this function to see what it gives us. And actually, so there's 9 combinations of species and islands, and it has counted all of these for us. It's actually instructive to see how we could do this with dplyr and see if our answer is the same as what dplyr would give us, because in the normal course of things, this is not how we would perform this task, because dplyr already provides us with functions that do this kind of task. So I could take penguins and I could pipe it to count, because count takes combinations of variables and then counts how many occurrences of that combination of variables there are in the original data set. And so I can do species and island, and if I run this, now this is our data frame produced by our function, and this is the tibble produced by count, and the numbers look okay. There are 44 Adelies on Bisco, there are 52 Adelies on Torgerson, and 56 Adelies on Dream. So our function is working correctly, and of course this should show you the power of dplyr, where in just 2 lines of code I have accomplished something that would take me many more lines of code to accomplish. However, once again, there can be tasks that dplyr does not perform, where if we know how to write nested for loops, we could accomplish those tasks. Lastly, let's consider the situation where we have to repeat a task a number of times, but we don't know in advance how many times we have to repeat it. And the number of times you repeat it depends on the context of the situation. So for example, we could be simulating population growth with births and deaths and would like to stop the simulation when the population stops changing, that is, it reaches equilibrium. but we don't know beforehand how many generations it's going to take to reach equilibrium. For such situations, R and other programming languages provide the while flow control loop. And the syntax for while is, you say while, and in parentheses you give a condition, which is a logical expression, that a logical statement that returns either true or false, or it could be a logical scalar, followed by a statement or a compound statement enclosed in curly braces, and this will keep executing this expression, this compound statement, so long as this condition is true. As soon as this condition becomes false, the while loop will stop executing this statement and pass control to whatever is the statement that follows the while statement. Okay, so now let's use while to actually do the simulation of a population that's growing. And let's write a function that takes a starting population n0. It'll have a growth rate alpha, a death rate beta, and it will compute the population in each successive generation until the population reaches equilibrium. So how do we define equilibrium? When the change in the population between two successive generations is less than some number, the tolerance or tol, we will stop simulating. We'll say the change is too small. That means the population has reached equilibrium. It has stopped changing, and we can stop the simulation. And we will simulate this with the logistic model. And what the logistic model is, it says that the change in the population between generation G plus 1 and generation G is proportional to the population in generation G, and the proportionality number is R. Now, if this R is a constant, that means the population, and just for an example, if R is 1, the population will double each generation. However, this would lead to an exponentially growing population that will grow indefinitely. However, that's not how real populations behave. In real populations, as the population gets big enough, resources become limiting, and therefore this rate of growth, this R, goes down with population. And the simplest model that you can make is that this R is alpha minus beta times the population, so that when the population is very low, the growth rate is alpha, but as the population grows, the growth rate reduces with a rate beta. So we would like to use this model to simulate population growth, and the user will provide these parameters alpha and beta, and we don't know how many generations it's going to take to reach equilibrium, and therefore this is a good example to see how we can use while flow control statements. Okay, so let's write a function called pop growth, and this function will take the initial population n0, it'll take the growth rate, it'll take the death rate beta, and it'll take a tolerance, which is when the change in two consecutive generations is less than tolerance, we will say that the population has stopped growing, it has reached equilibrium, and we should stop the simulation. We need to track the population and we would need to compute so we would need to track the population in generation G, and we need the population in generation G plus 1. So we will need two variables. One will be the current population and the other will be the previous population. So let's say the current, the first, which is the previous population, is N0, because that's where we're going to start. Now, we will keep simulating the growth of the population so long as the current population minus previous population, so the change in successive generations, is greater than the tolerance. As soon as the change in successive generations becomes less than the tolerance, we will stop the simulation. And the current population is going to be determined from the previous population using this model. So we will say the current population is going to be previous population plus R times NG, which is the previous population. Now, what is this R? This R from this expression is alpha minus beta times the previous population. And so this line will take the previous population and then use this logistic model to give us the current population. We also need to track the generation. So let's initialize a variable for the generation, which will be initialized to a value of 1. And then once we have advanced, we should increase the generation number by 1. So we'll take the value in the generation variable, add 1 to it, and save it back in the generation variable. And this will allow us to construct a vector for the population. So this vector initially will have just one element and 0. And then once we have created a new generation, and we know what this new generation's population, we'll say pop generation is equal to the current population. And so the way this loop is going to work is that we have some previous population from which we use the logistic model to compute the current population. And then when we come back to the start of the loop, we will test whether current population or the difference between the current population and the previous population is bigger than some number. And so long as the difference is big enough, we'll conclude we are not at equilibrium, and we should compute the next generation. Now, one problem we run into is that, let's say previous population was 1000 and current population is 1100. In the next loop, previous population is still going to be 1000, and so the current population is still going to get computed as 1100. We need to actually update the previous population to the current population of the previous generation. And now previous population is going to be 110, so we'll get a new number for current population, and once again we'll check this condition, and so long as the change is big enough, we will again update the previous population and compute this number, so our population will change with time. Now, one problem we're going to face is that when the first time this condition is checked, the way we have written the code right now, there is no such thing as cur population, and so R is going to give an error for object not found. So we must also initialize the cur population, and we will initialize it to n0, just like pref population. But this will create a problem for us, because if in the first iteration cur pop minus pref pop, which are both n0, is going to be 0, and that's going to be less than whatever tolerance the user specifies. So we can circumvent this problem by having two conditions. We could say execute this loop while the difference in populations is greater than tolerance, or you are simulating the first generation. And this will ensure that even though initially the difference between the current population and pref population is 0 and less than tolerance, we will still execute the while loop in the first population, but then the current population will get updated according to this equation to some new value, and we won't really need the other condition after the first iteration. And now we have a vector called pops, which contains the populations in each generation. And let's save these populations and the generation number as a data frame. So we will say pops df is data frame, and the first column might be the generation, and how many generation the generation should be going from 1 through the last generation, which is the value of this variable generation after the while loop has exited. So we could just say seek generation, and seek generation will give us a vector starting at 1 and ending at the current value of the variable generation, which is how many generations have been simulated. Remember, we are doing this while loop because we don't know in advance how many generations it's going to take. And then we could have another column called population, which will be pops. And finally, we will return this data frame, and this will give us when we call this function pop growth, it will return a data frame in which one column is the generation number and the second column is the population in each generation. So now let's call this function, and let's start with an initial population of 12. Let's start with alpha of 1. Let's start with a beta of 0.001 and a tolerance of 1, which is saying when the change in population in successive generations is less than one individual, then we will say they have the population has reached equilibrium. And we can pipe this data frame that will be returned by pop growth to ggplot, where in the aesthetics we can put generation on the x-axis and population on the y-axis, and perhaps we will plot this with geom point. And now when we run this function, we get this plot of the population with time. It starts out as 10 and it grows exponentially, but as the population rises and resources become limiting, the rate of growth reduces so that eventually the population stabilizes and is at equilibrium and it stops changing. And what if alpha was 0.6? What would the curve look like? What if we had much faster reduction in growth rate? What does the population look like? And so on. And one should play around with this model to see how changing alpha and beta, or the initial population, changes the profile or the pattern of growth of this population.